And they've had some anomalous features. Fun. I love it. The first of these, Oumuamua, discovered with telescopes in Hawaii. So that, as it came through the solar system, we said, all right, we know what trajectory an object with that speed and that direction coming in should take as it rounds the sun. Then there was the actual trajectory, which was different. Like, whoa. Well, comets have a way of outgassing when they get near the sun, and that puts an extra little sort of force on their arc of motion that has them move in ways that are not purely gravitational. And that's true for all comets. So we thought maybe that's outgassing. But suppose you look and there's no outgassing. So what's going on? Well, that's fun.
So why did an object from another star system refuse to follow the path gravity predicted? In basic physics, once you know an object's position, speed, and the gravity acting on it, its route through space is fixed. That route is called its trajectory. When astronomers tracked this interstellar visitor, they found that after it swung past the sun, it was drifting away ever so slightly faster than gravity alone would allow. That extra nudge is what we call a non-gravitational acceleration, a change in motion caused by something other than gravity, like gas jets or radiation. What made this puzzling is that the object looked completely inert, with no obvious signs of activity. So, the core mystery became, what invisible force was pushing it, and what does that say about how we interpret strange data? One natural explanation astronomers have investigated is something so gentle you never feel it on your skin: the push of sunlight itself. Light is made of particles called photons, and photons carry momentum, meaning they can transfer a tiny shove when they hit or bounce off a surface. This effect is called radiation pressure, and on a spacecraft equipped with a thin reflective sheet, a solar sail, it can gradually change the craft's speed and direction. This has been experimentally demonstrated with missions in our own solar system. For a typical chunky asteroid, radiation pressure is negligible because it has a lot of mass for relatively little surface area. But if an object is extremely light for its size, more like a sheet than a solid rock, and the same sunlight can noticeably alter its path over millions of kilometers. That raises a provocative possibility. Perhaps our interstellar visitor behaved oddly, not because it was breaking physics, but because it had an unusually large area compared to its mass, making it surprisingly easy for starlight to push. But how can we talk about shapes, spins, and subtle forces when the object was never more than a pinprick of light in our telescopes? Astronomers never saw a resolved image. Every artist's drawing of a long cigar or a flat pancake is an illustration, not a photograph. What we actually measure is brightness as a function of time, a record called a light curve. As the object tumbles, different amounts of its surface face us, so the reflected sunlight rises and falls in a repeating pattern. For this particular visitor, the brightness changed by a large factor, implying it was either highly elongated, highly flattened, or had very strong contrast between bright and dark regions on its surface. Because we only watched it for a few weeks before it became too faint, many different shapes and compositions can reproduce the same light curve, which means several physical models, thin shard, fluffy aggregate, volatile-rich fragment, can all plausibly account for the same weird trajectory. The fact that our first interstellar visitor looked extreme might not be a cosmic coincidence at all. Whenever you have a detection threshold, like a minimum brightness that a survey telescope can see, you introduce what scientists call a selection effect. Your sample is biased toward things that are easiest to detect, not necessarily the most common overall. Imagine you stand under a streetlight at night and count people. You might conclude that almost everyone walks only where it's bright, simply because you never see those in the dark. In a similar way, among the vast sea of rocks drifting between stars, the earliest ones we notice are likely to be unusually reflective, unusually large, or subject to extra forces that alter their paths and keep them in view longer. That means discovering something that looks 1 in a million on first encounter is exactly what statistics would lead you to expect, and it softens the shock of that non-gravitational push. So, what kind of evidence would actually force us to say, this cannot be a natural object? For a technological origin, you would want hallmarks that are hard to mimic with ordinary physics. For example, repeated radio or laser signals encoding information, or motion that looks deliberately controlled, sudden changes in direction, hovering, or synchronized maneuvers with no natural cause. What we observed instead was a smooth, continuous path consistent with a tiny, steady force, exactly the sort you get from gentle outgassing or radiation pressure. Outgassing is when ice or frozen gases inside a body warm up and turn into vapor, escaping as jets. Comets display this dramatically as visible tails, but if the gases are made of species that are hard to see from Earth, you can have thrust without a bright plume. Several proposed models use familiar ingredients, water ice, carbon dioxide, nitrogen, or even very porous, fluffy aggregates of dust, to generate a small push with little visible signature. From a reasoning standpoint, these scenarios stretch our picture of what interstellar debris can look like, but they do not require adding an entirely new category of agent, such as alien engineers, to the universe. In the end, the rebellious path of that interstellar rock tells us more about our ignorance than about alien engineering. The measurements are well described by gravity plus a modest additional force, likely from sunlight acting on a low-density object, or from subtle outgassing of materials that our instruments were not sensitive enough to detect. The unresolved questions are about the object's internal makeup and geometry, not about any breakdown of the laws of motion. Philosophically, that is powerful. The anomaly is not a glitch to be hand-waved away, but a prompt to revise our assumptions about what kinds of fragments other star systems can fling into space. As new wide-field observatories scan the sky far more deeply, we expect to see many more interstellar visitors, and their collective behavior will tell us whether this first one was an oddball or an early glimpse of a whole new population. So, the answer to our opening question is that the object did not truly defy gravity. It exposed the limits of our intuition and reminded us that the universe is under no obligation to send us familiar examples first. We have to expand our understanding to meet what is actually out there. Like if this was interesting, and hit the subscribe for more.